Hello, this is my presentation for my graduation project from Bogazici University Computer Engineering Department. My project is about a theoretical study on DFAs and a specific subset of binary regular languages. So DFAs, the discrete finite automata, are one of the most simple computational models. And there are still a lot of avenues for exploration about these models. One such topic is the amount of maximum incoming transitions to a state per symbol in the alphabet. I will explain the definition with an example later on. But based on this metric, we can construct some subclasses of the binary regular languages. And formally, a binary regular language is said to be in the subfamily or the class EI if there is a DFA recognizing it with no more than I incoming transitions per symbol for all of the states. So let me explain this with an example. This DFA recognizes the language of strings containing BB as a substring. So in this machine, as we can see, there are three states, and one of these states, the Q2 state, has two incoming transitions with the symbol B, one from the state Q1 and one from the state Q2 itself. So because there is such a state, then this DFA is only enough to say that this language recognized by this DFA is under the E2 class. Another example here is this language of strings that do not end with A. And this is a more simpler machine with two states, and in here similarly both the Q0 and the Q1 state have incoming transitions with the symbols. Q0 has two incoming transitions with the symbol B, and Q1 has two incoming transitions with the symbol A. Similarly, this DFA's existence is only enough to say that the language recognized by this DFA is in the E2 class. And now we can go to a more complex example of a non-E2 class language, which is the intersection of these last two languages. So it must contain BB as a substring and also do not end with A. In this machine, as you can see, the state Q2 has actually three incoming transitions with the symbol B from Q1, Q2, and Q3. Now, what we cannot say just by looking at this machine is that this language is not in E2, because you have to prove it. You have to mathematically show that just by giving the minimal DFA of a language, we cannot just claim that looking at this machine, it cannot be recognized by another machine that doesn't contain such states. So my key findings include energy classes of these languages have some closure properties, and I showed that the E1 language subfamily is closed under complements, unions, and intersections. These are simple operations of regular languages generally, and also apply to binary regular languages. E2 language subfamily is closed under complements as well, and the E2 language subfamily is not closed under unions, intersections, and concatenations. As we saw in this example, these two E2 class languages, well, after giving the proof, the intersection of those two languages is not in the E2 class. So to conclude, the main goal of my work was to provide a stepping stone for future work about the general theory of energy class subfamilies, as I mentioned. And such a theory could explain how one can construct some languages that are not in the E2 class from the E2 class languages through the operations that I showed to be not closed under the E2 class is not closed under some of these operations, and there are more complex operations, and a future work can focus on to see if there is a way to construct all of the languages that are not in the E2 class from more fundamental parts, basically in E2 class. Additionally, an easy method for determining which class any given language from just by looking at the minimal DFA of that language would be a great finding for any future work. Thank you for listening.